Welcome. So, today we're going to get into a really fascinating theory that's been making some serious waves in the AI community. It's a potential answer to why a new generation of AI models seems to reason in a way that's, well, fundamentally different and a whole lot deeper. Okay, so let's just start with the central question, right? We've all seen AIs get bigger and better at just spitting back information they've learned, but how do they make that incredible leap to genuine, novel problem solving? That's the mystery we're unpacking today. And yeah, that mystery actually has a name in the research community. They call it the Mythos mystery. It's named after the models that seem to show off this strange new ability. So here's the core observation. Some models seem to be punching way above their weight class. They're tackling these complex, multi-step problems they have never seen before, and they're doing it without needing to be astronomically larger than other models. It really hints that something is just fundamentally different under the hood. So what could that difference possibly be? Well, the prime suspect, and what we're going to focus on, is this really compelling idea called the looped transformer hypothesis. At the very heart of this is an architecture called a recurrent depth transformer, or an RDT for short. Now, instead of building a giant skyscraper of unique processing layers, imagine an AI with a smaller but much more powerful set of layers that it reuses. It loops through them over and over again to think deeper about a problem. It uses the same core programming, the same weights, for each loop, which allows for much deeper thinking without adding all that extra complexity. You know, this analogy really makes the difference crystal clear. A standard AI, it's like speed reading a massive book, just one time. It'll get the gist, but it's probably going to miss the nuance. A looped transformer, on the other hand, is like rereading a single, dense chapter multiple times. With every single pass, it uncovers new connections and builds a much, much deeper understanding. So how's it actually work? Well, the theory proposes a three-stage process. First up, you've got the prelude, which encodes the input just like a normal transformer. Then comes the magic, the recurrent block. This is where a small set of layers is looped through again and again and again. And finally, you have the coda, which takes that deeply processed result and forms the final output. And this quote right here illustrates a really crucial point. This isn't the AI thinking out loud, generating text step by step. No, this is a rapid internal process. All of that deep iterative thinking happens silently in an instant before a single word ever gets generated. It's happening in what's called latent space. Okay, so that's the theory, but what about the evidence? I mean, why do researchers really believe this is the key to the mystery? Let's take a look at the clues. Okay, the first piece of evidence is called systematic generalization. These models, they don't just memorize things. They seem to suddenly grok or truly understand the underlying rules. And that's what allows them to solve entirely new combinations of problems they were never trained on, which is a feat that standard models really, really struggle with. The second clue is, frankly, even more amazing. It's called depth extrapolation. So get this, you can train one of these models on problems that take, say, 5 steps to solve. Then, at test time, you can give it a 10-step problem, and it can solve it just by running more loops, just by thinking a little deeper. And this brings us to this really cool idea of latent thoughts. You can think of each loop as one step of reasoning. But because it's all happening internally, the model can explore multiple paths at the exact same time. So it's not just following a single train of thought, it's basically conducting an internal brainstorming session to find the absolute best possible solution. And here's the kicker. Parameter efficiency. I mean, the slide just shows it perfectly. A small 10-layer model that loops 10 times can actually achieve the performance of a massive 100-layer model. You get all of that incredible reasoning power, but with a fraction of the size. The depth it's essentially free in terms of parameters. It's wild. So if this architecture is so powerful and so efficient, you've got to ask, why isn't every AI built this way? Well, for years, there was a critical, show-stopping flaw. The simple truth is that these models were an absolute nightmare to train. They were incredibly unstable, and they often failed in just spectacular fashion during the training process. And that, of course, made them completely impractical for any real-world use. They would tend to fail in two main ways. The first is residual explosion. This is where the model's internal signal just gets amplified with each loop until it's just noise. Think of a distorted echo getting louder and louder. The second is loss spikes, where the entire training process would just suddenly collapse and fail completely. Poof, gone. The breakthrough came from a huge change in perspective. By treating the loop not just as a stack of layers, but as a mathematical dynamical system, researchers found the key. They basically discovered a stability dial, a value they call the spectral radius. And if they could just keep that dial below 1, the system would remain stable. And this insight led to a real solution, likely based on what's known as the parquet architecture. It very cleverly constrains the model's parameters so that the spectral radius is guaranteed to stay below 1, just by its very design. So the crucial point here is this makes the model robust and finally allows it to be trained cleanly and reliably. All right, now that we've seen the theory, the evidence, and the solution to its biggest problem, let's zoom out and look at the pretty profound implications of this whole new way of building AI. And the results are absolutely stunning. This slide here shows a real-world example, a 770 million parameter looped model achieving the same quality as a 1.3 times billion parameter standard model. That is the same capability with roughly half the size. Just let that sink in. So let's just put it all together. This table gives a fantastic summary. The architecture is a recurrent depth transformer. It reasons through these silent internal updates, and critically, it is structurally biased towards reasoning over simple memorization. That trade-off right there is key to its power. And of course, the theory goes even deeper. There are other key innovations to talk about. For instance, loop index embedding, which allows each pass of the loop to do something slightly different. There's an overthinking fix to help the model know when to stop. And you can even combine this with mixture of experts to give the model a huge breadth of knowledge. But like any design, there's always a trade-off. This architecture is an absolute genius at reasoning and putting ideas together, but its Achilles heel can be simple factual recall. And this actually matches what we sometimes see as users, an AI that can solve a complex calculus problem, but then every now and then stumbles on a really simple fact. And that brings us right to our final thought. The big takeaway here is this. What if the next giant leap in AI isn't just about more data or more parameters? What if it's about building models that can truly think deeper? If that's the case, what new frontiers does that unlock for all of us?